Hello students, welcome back. In this new video, we are going to talk about logic gates. Now, what exactly are logic gates? Well, previously we talked about computer architecture. We started from there. Then we talked about how data actually comes into the computer system and then out of the computer system. In between, some processing takes place. How does the processing takes place? Well, with logic gates. So, as we mentioned previously, right, how electronical device actually detect the state and the data is by checking whether there's electrical pulse or there's no electrical pulse. So it's either on or off. So when we talk about processing the information, we are taking this electrical pulse in, and then based on their combination, right, we decide the output. So you have a logic gates. They actually enter this logic gate. The logic, based on some rules, will decide what to release into the output. Okay, so how does it work? Right, so as you can see, we need to begin by talking about Boolean logic. So what's Boolean logic? Now, Boolean logic actually look at things in two ways, right? So either 0 or 1, true or false, on or off, high or low. Now the high and the low here in our context usually means high voltage, low voltage. It could be that. And then yes and no. So there are many different ways to represent Boolean's value. But in a nutshell, Boolean simply means a data type representing either true or false. Two binary state, right? So that is the Boolean logic. So when we receive data, when the computing system receive data, we receive them in Boolean form. So to understand how this thing works, we actually can create something called the truth table to help us to actually figure out how it works. So for a very simple example, you can see on the screen right now, right? There is a input and there's output, right? So in table 3.2.1, the first one, we have one input, we call it input A. And then based on the setup of our logic gates, we will have a certain output. Now for table 3.2.2 is what happens when we have two inputs, right? So two connectors going in to the logic gate, and depending on the way it's set up, we have all these different combinations. So when there's two input, you can see that there's four different combinations. We come out with different set of outputs, and when there's three inputs, it gets eight different combinations. So from 2 to 4 to 8, you get the idea, right? 2 to the power 1, 2 to the power 2, 2 to the power 3. So this is what happened, right? So based on the number of inputs going into a system of logic gates, and then depending on the combination, we get the output. So what exactly are logic gates? So let's go into a bit more detail. So in this first section, we are going to begin by looking at a few of logic gates. Okay, they are called the AND, OR, NOT, NAND, NOR, XOR, right? We will deal with them one at a time. So what exactly are logic gates? Logic gates are electrical circuit, right, that performs logical operation based on one or more inputs and produces a single output. So we have a circuit, we have all the inputs going in, and then based on the setup of the circuit, the logic gates inside, we have an output, right? So the logical operation, that's another word that you need to know, is an operation that acts on the binary input. So those inputs are binary, right? And they produce an output according to the laws of the Boolean logic. So again, the output will also be in the Boolean form, either 1 or 0, true or false. Okay, so that is the structure that we are looking at. So here's the first one that you should look at. It's called the AND gate, right? Just like the English word AND, right? So in this case, we have two inputs. You can see the symbol. We have A, we have B going in, and we just use the letter Q to represent the output. So the AND, the symbol, as you can see on the screen as well, okay, we can actually write it in this sort of a something like algebraic form, but it's actually called the Boolean statement, right? So Q equals to A dot B. So this really means the AND, right? So this is Q equals to A and B. How does it work, right? So if you look at the truth table on the bottom left of the screen, you can see that when the input are false and false, 0 and 0, then it's false, right? If it's either one of them is positive, the other one is negative, or either one is true, the other one is false, it is still false. But when both is true, then the output is true. And that is what we mean by AND, right? When we say A is true and B is true, it means both of them must be true in order to have the truth result. So to help us to visualize, there's one example here, right? So if we are talking about somebody who can sing and can dance, right? So can sing and can dance, when we describe someone this way, it means that they can sing is true, can dance is true. Therefore, can sing and can dance. If they can sing but cannot dance, then it's still false, right? So that's the example we have here to help you to visualize what's going on. So that is the AND gate. So we have a simple AND gate. Two inputs go in, we decide the output if both is true. The next one is the OR gate. Again, not difficult to understand because it relates directly to the language that we use, right? So when we have A or B, it means that either one is true, good enough, right? So the Boolean statement will be written in this way, right? We use the symbol plus addition symbol to represent OR. So the output is A or B. So as you can see from the bottom left of the screen, the slides, right? You can see here, same thing. If as long as one of the input is true, the output is true. Okay. So to help us to visualize how it works, right? So for example, we have a situation where we are asking whether there's a burglary, for example. So is the window open or is the door open that allows a burglar to come in? So as long as one of these is open, then yes, okay, we have an opening for the burglar to come in. But if both is true, it still qualifies, right? So if A is true and B is true, it also means that A or B, right? It qualifies. The only instant is when it is false and false. When it's false and false, no, right? It's not. Okay, so this is the second gate, OR gate, not difficult to visualize, I hope. The next one is even easier. It means not, right? So as we can expect, not means opposite, right? So what happens in this particular one, the symbol looks interesting. It's a triangle with a little circle. You will see that the little circle at the output area can be used later on as a combination with the others to represent that there's actually a not over there, right? So in this case, whatever the input A is, the output will not be A. So it reverses it, right? So it's quite straightforward. When the input is 0, the output is 1. When the input is 1, the output is 0. So that's the NOT gate. It simply reverses the state of the input to the output. Now this is the next one that's things get a little bit more interesting. So we have the NAND gate here, right? So if you look at the symbol, the NAND gate actually looks like the AND gate with a little circle at the output area, and that circle represents the NOT. Okay, so you can see in the bottom, just below here, okay, what happened is you can think of the NAND gate as a combination of the AND gate followed by the NOT gate. So what it does is the NAND gate, really it means not AND, right? It's the opposite of AND. So you can see the Boolean statement is written in this way. The output Q is A and B, and then there's a bar on top. Okay, the bar on top here actually represents not. Okay, so if you look at the truth table on the bottom left of the slides, you can see it's the reverse of the AND, right? So if you look at the combination, the AND gate gives us 0, 0, 0, 1. Whereas for the NAND gate, it goes 1, 1, 1, 0. So the only one that we reject is not AND, right? When it's AND, we do 1. The rest, we want, right? So that's how it works. So following the same concept, we introduce the next one. This is the NOR gate. Now the NOR also often used in our everyday language, right? So it simply means not or. So similarly, you got the symbol. It looks like the OR gate with the not followed by the not. So we use a little circle here to represent. So the Boolean statement is written in the same idea. The output Q is A or B with a bar on top, which represents not. So the truth table, as you can see, okay, is actually the opposite of the OR, right? OR, as long as one of it is true, we want it, so it's 0, 1, 1, 1. However, the NOR gate goes the other way around. It's 1, 0, 0, 0. So when we say something is neither A nor B, right? So it means that both must be 0, right? So that's the same concept, and it fits very nicely with our daily usage of the word NOR. Okay, this one is interesting. XOR, right? XOR. The X here basically means exclusive. Okay, so the symbol is looks like the NOR gate, but there's an extra line at the input area. So the Boolean statement looks interesting. We have a symbol that looks like the addition, okay, which is the OR, but we put it in a circle. So what this does is that we only want the cases where only one of the input is true, the other one is false, right? So it cannot be both true at the same time, cannot be both false at the same time, right? So this is a little bit different from the NOR, it's a little bit different from the OR. Okay, so this one, that's why it says exclusively OR. When we say A or B, must be A or B, cannot be both accepted, right? Both true we don't want. So a good way to visualize this is talking about ordering coffee or tea, right? So when we go for a meal, when we order the beverage, usually if we are thinking about something with a little bit of caffeine, it's either coffee or tea, right? But of course, when we say or, it means, oh, give me coffee and tea together also, I'm happy. No, right? We just only one cup. Okay, so in this case, either the coffee is true and the tea is false, or we have the situation where the tea is true and the coffee is false. So this is the only situation that is acceptable in this case, right? So we can think of it in this way. So we have looked at quite a number of gates already. I hope you get used to them and remember them, how they work. With more practice, you should, right? So coming to the next section, we're going to talk about logic circuit. So let's look at the learning outcomes. Logic circuit says, right, we are supposed to learn how to represent logic circuit using either the logic circuit diagram, right? So that's why just now we learned about all the various symbols, because we should know how to actually draw them. When we plan a circuit, we actually do some drawing like this, right? Or Boolean statement. So you can write it sort of like algebraically, but it's different, right? It's called Boolean statement. And to be able to convert between these two way of representation, so if I give you the drawing, the diagram, you should be able to convert it to the statement. If I give you the statement, you should be able to convert it to the diagram, right? And the next thing that we should learn from, should understand from this chapter, is to be able to construct the truth table, okay, given the circuit, right? So either you receive the diagram form or you receive the statement form, we can construct the truth table. And the truth table becomes important because the truth table is where everyone can refer to very easily, and from there we know and can predict the outcome when we have the of the output when we send our input into the computer system, right? So talking about the logic circuit diagram, some keywords. Let's look at the keywords again. Logic circuit, right? The word circuit, I think you more or less heard of it before. So what does it really mean in terms of computing, right? So the logic circuit is a circuit that consists of only one logic gate or multiple connected logic gates. So basically, when we look at the circuit, you know, the green color thing that you see if you open up all your electronic devices, all the wires, everything there, they are actually formed by really tiny little logic gates everywhere. Right? So engineers who design this, you know, they actually design to see what's the most efficient way to actually place all these logic gates. So when all these logic gates comes together, you create the logic circuit, right? And the logic circuit diagram is a visual representation using symbols to show how all the components and how all the logic gates actually connected together to form this circuit. Cool, right? So here's a simple example of where we use more than one logic gate to create a circuit, right? So here we have two NOR gates, right? So what happened is this is a system where we take in three inputs. So we probably have three wires, with signals going into this circuit. And then we have input A, input B, input C. Now input A and B goes into a OR gate, and the result that comes out of this logic gate is called the intermediate input, because this output can be used to go into another logic gate. So logic gates is not just standalone. Just now we talked about system of logic gates. So you have logic gates with the connection everywhere. So this really depends on the skill of the engineers, depending on the specification, what do you want to achieve. They can design really very fantastic and very elegant circuits. So this one's easy to understand. So the output of one logic gate can be used to feed as the input of another logic gate to create the final output, right? This time round, the output D and also the input D, right, goes together with the input C to create the final output Q. Okay, so you can see how it is. You can visualize what's going on. So what happened is this, right? We want to figure out how this thing works. So the overall circuit here, right, has three inputs. So as we have spoken earlier, if it has three inputs, then the inputs, how many combination we get? We get 2 to the power 3, 8 possible combination, right? So as you can, that's why when we construct the truth table, well, 8 rows, excluding the heading. So 8 rows, you can list out all the different combination. So to figure out how this entire system work, right? For example, we have a system here where A and B goes into an AND gate, and then the output D and another input C goes into the OR gate. So on the bottom left of the slides, you can see we have our input A and B, all the different combination, we list it out. And we want to, from here, right, figure out what is the intermediate input D first, right? So we can work out the D is an AND gate. Therefore, the only case where I get a 1 is where both A and B's are 1, right? So the last 2 rows over here. So from here, I fill it up. Now I can see my intermediate D, input D. And then just looking at C and D, we know that it goes into the OR gate. We can work out the output Q. So this is the situation, right? Output Q. So 0, 1, 0, 1, 0, 1, 1, 1. So from here, we get a full picture where we look at all the input A, B, and C, right? Which is the true real input into this circuit. We know that which combination gives us which output. So it becomes very clear on the final truth table. Will you be required to actually know how to construct such truth table? Yes, if you want to be good at computing, you should learn how to do this well. Okay. Right. Let's talk a little bit about Boolean statement, right? So like the logic gate, a logic circuit can be represented by Boolean statement as well. And Boolean statements are useful in 2 ways. It's written over here. They can be evaluated using the truth table to determine the output of a circuit. So people can actually look at the Boolean statement, and people who are familiar with how all this circuit works, they know from there how the truth table will look like, right? And then they can determine the arrangement of the logic gate. So sometimes there's a specification from the engineer say, this is what we want based on the Boolean statement, and then after that, the junior engineer or someone else take it, and then they figure out and they design the requirement of the circuit, right? So of course, as we just like mathematics, when there's a lot of different operations, there need to be an order, right? Which one goes first? Multiplication goes before addition, for example. So just like mathematics, when we talk about Boolean statement, with the way we write it, there has to be some kind of ordering as well. So it goes like this, right? From the Boolean statement, the first operation that takes place is the parentheses, sometimes also known as bracket. So it works like mathematics. Anything inside the bracket, we sort it out first. Well, the next one is the NOT, right? The NOT gate, the one that flip over. So in Boolean statement, is the bar on top. We think of it like, like to the power like that. It's sort of like the index. So we actually sort that one out next. And then we have the AND gate, which works a little bit like multiplication, come to think of it. And then we have the OR gate that we sort out last. And just like in mathematics, we use the symbol addition, right? We know that we sort that one last as well. So Boolean statement also follow the same logic. So if you're familiar with your Beamer's rule, Bodmer's rule, whatever you call that in mathematics, the same idea applies here. Okay. Right, so here's a little example. So we want to construct, consider the Boolean statement here. So we have the output Q is actually A. Well, the dot there represents, I hope you remember, it represents N, right? So it's A and B, or in brackets, A and C. So which one do we sort out first? Well, we sort out the brackets, right? The parentheses first. So again, there are three different inputs here, A, B, and C. So we have 8 rows excluding the heading. List out all the different combination. Then we have intermediate input, right? Because what happened over here, we have A and B, we have A and C, right? So A and B, what do we get? Okay, so you just ignore C for the time being, look at A and B, and using the AND gate logic, we fill it up to get intermediate input D. And then using the intermediate input E, we look at the row A, column A and column C, ignore the input B for the time being, look at the combination, again it's an AND gate here, so we fill up the necessary. So once we have this, what happened is, the A and B give us the D, A and C give us the E, and the D and the E is actually the OR in between, right? As you can see, is AB or AC. So now we look at the intermediate input D and E. Just looking at these two columns, we can figure out what is the final output Q, right? Just look at the combination for OR gate in this case. So once we settle down, we fill out the entire truth table. We can see now we declare, from the input A, B, and C, which combination will give us the necessary output. It becomes very clear, right? So this is the situation, right? So let's go on and try to construct the Boolean statement this time around from the truth table, the other way around, right? Just now we have the truth table. Now this time around, let's take a look. This is a truth table that's given to us. Can we work the other way around this time around, get the Boolean statement? Well, what happened is first thing we want to take note is how many inputs, how many outputs. So 3 inputs, 1 output, very good. 8 rows makes a lot of sense, right? So the first thing is to really determine the combination which will result in an output of 1. So what do I mean, right? So the output of 1 is over here where we have 0, 1, 1, and then another one over here which is 1, 1, 0. Okay, so you can see here, right? These are the two combinations that will give me the output of 1. Okay, so I'm going to create an AND term for each combination that results in an output of 1, right? Since these conditions needs to be all present for output to be 1, we should AND them together, right? Note that A bar, okay, the line on top, is used to represent A is equal to 0, because when A is 0, A bar will give us 1, right? So what it means is that we can write it in this way first. So A with the line on top, and then in this case C with the line on top. So this means 0, 1, 1 and 1, 1, 0. And take a look at the truth table. That's true. 0, 1, 1 give us the output 1. 1, 1, 0 give us the output 1. So this is a situation, right? So first, step 1, we look at the truth table, identify the situation where the output is a 1, and then we write it in this form. Okay, so then you see what we can do next. Let's go. Step 3, right? We OR the AND terms together, right? So since either of these two inputs will give us the result of 1, right? These are the two combos that will give us the 1. We should join the partial Boolean statement together using OR, right? Thus we obtain this situation. So just now we have the A with the bar on top, then BC, and then we have the A, B, and then with the C bar on top. So this is our 0, 1, 1, if you can see my mouse cursor, and then this is my 1, 1, 0. So I OR them, right? Because as long as one of this combination is around, I will get the 1. So I OR them, right? So it is this combination or this combination. Is nice, right? So over here, quick check, there's a key term here, sum of product, a Boolean statement where the AND terms are ORed together. So this concept, okay, has a special name. It's called the sum of product, right? So we yeah, these are products, right? So we sum it up. So this form of representation where the n terms are all together, okay, has a name, right? Sum of product. Sometimes the abbreviation is used, SOP. Now, of course, this is what we get from here actually is enough to create our Boolean statement or our diagram. But is there a way to actually simplify further? Yes, there is, right? So let's take a look. Um, Sorry, let's go back a little bit. So there is actually a possible to sort of like mathematics have B as the common factor. It seems that is we are not using that for the time being. So we'll leave that for the future. I think that one is for the more advanced design of the Boolean. We'll talk about that when the opportunity comes about. So let me just continue with this deck of slides that have been prepared. Right. So the next example, right, is we want to construct this logic circuit diagram from Boolean statement. Okay. Same idea, right? So we have the Boolean statement here. Q is A and B or C, right? So we start by drawing the AND gate, right? A and B, A and B. So A and B looks like this. And then the result of A and B, which is over here, right? The intermediate, the output of A and B, is all together with the input C. So we have an OR gate here, and the third line at the bottom, that will be an input C. So this is a very simple, straightforward translation from Boolean statement to the diagram. Okay. Well, you will have more practices, definitely. Today is just to give you the overview and the theory part. So with more practice, all these things will come more naturally to you. Right, we have another situation here, right? So this time round, right, we are given the diagram. Can we obtain the Boolean statement? Sure, why not, right? So again, we look at this and we can see that, oh, over here, we have A or B, and then the result is actually another OR here, C or D. Okay, so what we can do is from here, we can take a look. We can start from the output Q and realize that the output Q is actually C or D. So you can write down Q is equals to C or D, or in this case, you can also write it as D or C. So D or C over here. Then we pull it back and realize that D is the intermediate input here, and D is the result of A or B. So we replace the D with A or B. So D equals to A or B over here. Well, you see me using the word or here, but in the Boolean statement, you use the symbol plus, all right? Okay, yeah, so that's a situation. So putting them together, we have this situation. The output Q is actually A or B, right? A or B goes first, and then whatever the result is, which is D, you OR with C. Quite cool, right? Okay, so finally, here's another more complicated, slightly complicated example, right? But still, if we already understood what's going on, we can do this. So here we have a situation. You can see the diagram, figure 3.13. Okay, there's a NOT gate there, there's an OR gate there, there's an AND gate there. So we are just trying to have the different type of gates, the combination. So same thing, we are going to start with the output. This time around, the output is called output Z, right? So output Z is actually D or E. So we can write it down, Z equals to D or E. Then we figure out where the D and E come from. So if you look at this, D is actually not A, right? So A goes through the NOT gate to get D. So D is not A. So NOT, we use the bar on top to represent. So D is not A. And then E, right? E is actually B and C. So we replace the E with B and C. So putting them together, replace the D and E with the actual inputs of A, B, C, we get not A plus, okay, or we can use the word or, then B and C. Cool, right? Okay, so I hope with this you have a clear idea of how all these Boolean logic works. So let's recap. There are three things you need to know: the Boolean statement, the Boolean diagram, right, as well as a truth table, and we need to be able to obtain the other formats and the way of representing them from one to another, to convert them from one to another. Right, next one. Just now earlier I was talking about the sort of the common factor idea. So here is coming, right? So some basic facts that you should know, right? That we can actually manipulate a Boolean statement, right, using associative and distributive property. So this associative distributive property, okay, they are listed here, okay. And sometimes some of them are called the De Morgan theorem. This one I will share them in more detail in other occasion. Okay, so these are some clear, straightforward properties you can see here, right? Annulment, what does it mean? A and false is false, right? So then after or A or true is true, it makes a lot of sense, right? So these are some of the things we talk about. So the bracket ones that I was talking about is somewhere over here, right? So it's a distributive law, right? So A and B or C, right? What happened is this is the same as A and B or A and C. So what happened is the A can actually be distributed. So from here you can already see, right, that if I were to put this as a circuit into a circuit, I can either use one AND gate and one OR gate to create this situation on the left hand side of this equation. I don't know if you can see my mouse. Or I indeed on the right hand side is a situation where I have two AND gate and one OR gate. So by using distributive law, I actually reduce the number of gates I actually need and achieve the same results. So the idea of all these different statement, how you manipulate them, how you design them, when you become more skilled with designing a logic circuit, right? That is where all this comes into play, right? We actually manage to find some way to be more efficient, design your logic gates better, and that's one of the reason in the early days how circuit boards get smaller and smaller, because the engineers gets better and better at trying to figure out using less logic gates. But of course there are other factors in play. This is just one of the factors why circuit boards get smaller and smaller over the years, right? So over here they have a little example, right, how these properties can be used to prove identity. So yeah, proving, right? So down here, if I have A and B or A or B, right, I can actually show that this one will just give me A. So it's like I have two inputs, right? But then actually it's redundant, because no matter what the input B is, the result will just follow A. And we can prove it sort of mathematically, right? You can see here A and A or B, right, is the same as A or false, right? 0, we can call it false, and A or B, right? So you see it makes sense. And then using the distributive law, we can distribute the input A out. So A or, then we have false and B. Now false and B will always be false, right? So it is A or false, which is just A, right? So this is one way we can prove it. Another one, interesting one, is at the bottom of the slides. You can see that this one is also quite common sense. Not A, right? We know it's the reverse of A. So not A give us A. So this is, I thought it's interesting that we have this as well, because sometimes there will be people who design the circuit board and then you put NOT gate followed by another NOT gate, which actually serve no purpose. So you can just clean up and make the whole thing a little bit more efficient. Right, moving on to the next section, solving system problems. So we can actually solve system problems using logic gate. So what do I mean, right? So here we have a little example, motion sensing lights. So sometimes you go into a room, it's dark, but then there's sensor, and then you move your arms around, wave a little bit, the lights turn on, right? So one example of how it works is that there's actually a logic gate in place, right? So there are two inputs going on here, right? Input A, input B. What are they, right? So input A is can be said to be the motion sensor. It sends whether there's a motion. If it detects a motion, the input is a 1. If it doesn't detect any motion, the input is 0. And then the input B, right, is actually the light sensor. So when it is bright, daytime, those motion sensors to turn on the lights. If it's already very bright in the daytime, you wave your arms, it is still energy saving. So when it is bright, you can actually configure it such that when it's bright, the input of B is 1, when it's dark is 0. So what happens is this is the situation, right? So when it's bright, you reverse the NOT gate, and then you got the intermediate C, it goes into AND gate, and the result will decide whether it's switched on or not. Okay, so how does this make sense? Well, sometimes it's quite difficult to tell based on the diagram, right? Which is why we have truth table. So if you look at the truth table, then the whole thing makes a lot of sense, right? So we can see the Boolean statement is here, fine, you know how to convert them, and then from there we can actually get our truth table. So what happened is input A represents a motion. So you see when there's no motion and it's dark, right? The intermediate is 1, fine, but the output is no light, right? We don't need to switch it on when there's no motion. Okay. Second scenario, again, no motion, but it is bright. Well, I mean, if there's no motion, it's bright, we still don't switch on the light. Okay. Third scenario, there's some motion and it's dark. That's where I need to switch on the light. So output 1. Whereas when the scenario where there is motion, but it's already very bright, it's daytime, right? No need to switch on the light. So this is a simple system, as you can see, right? Something that many of us have experience with when it comes to motion systems. So you see, real life application, right? So yeah, so you learn all these systems, you can see there's real life application, very clear, right? So that's how it works. So this is another diagram to summarize what's going on with nice little icon. Sure, yeah, it's the same thing. I've explained this already. So you see, no motion, dark, lights off, right? No motion, bright, lights off. Motion, dark, lights on, and then motion but bright, lights stay off. There we go. Happy, right? Okay, here's another scenario to help us to see how this logic gate actually applies to the real world. So we have a car door lock, right? So when we want to unlock the car nowadays, we have a key, and they actually detect whether the key is around, right? Where the key is near the car say, okay, the key is near the car, you may unlock the car, right? So the input is A and B, right? So A detects whether the key is around and whether the key is turned, right? And then B, whether it has a signal. Okay, so it goes like that. This is the Boolean statement, right? Not A or B, right? That's the output. So how do we represent this in the diagram? You can see here, right? So we have the key switch, right? If the key is not there, the input A is 0. If the key is there, input A is 1. And then we have the sensor, right, to sense whether the right key is there. So if the signal is not there, well, input B is 0. When the signal is there, it's 1. And then it goes through what gate is that? This is a NOR gate, right? So a NOR gate. So going through a NOR gate, well, if it is A, NOR B, so what happens is if you have no key, no signal, stays locked. Definitely, right? If you're far away from the car and the key is not there, stays locked. But okay, if the key is not there, but it receives a signal, what is this? Maybe you have another way of having a signal, because nowadays with smart cars, sometimes you can unlock the car without the key. You unlock the car with the app on your phone. You receive the signal, unlock, right? Or you detect the key, but then your app is not on, but the key is there, so just unlock. Or the key is there and the signal is there, sure, unlock the car, right? Make sense? I hope it does. Okay. Another scenario, two-way switch. Again, you may have experience with this. So you have a system where maybe you have a lights, and then you can either use switch A to switch it on or off, or switch B to switch it on or off, right? So this is also very, very common, especially lights in a big room where you have switched in two different corners of the room, right? So this is the input for A, input for B, and then the output, right, for Q. So how does it work? Well, the output A is either A and B, or not A and not B. Okay, so this is how the circuit works. So you can see here, if A is off, B is off, then Q is on, right, and so on. Okay, so what happens if only one of them is turned? Well, it stays off. But if both of them is turned in the same direction, stays on. So what happens is you just flip one of them, either one of them, the status of the light change, right? So that is how the circuit can actually look like. You can work it out step by step. Okay, so with this, I hope you have a better understanding of Boolean logic as well as how all these logic gates work. So in a nutshell, what you need to know is that the circuit that we talk about all the time, circuit boards and so on, how the processing works. Know you have input going into this system here. It goes through all these logic gates depending on how the engineer design it, and then you have the output that we want, right? So that's a very simplistic way to understand it. And we learn some of the basic component of the logic gates. You will get some practice on how to actually design some logic gates. Okay, so that is the main idea behind this chapter. So I hope you learned something today. Have a nice day.